Good morning, everybody. So yesterday we started our Earth's history unit and kind of did a brief overview of life on Earth and the development of Earth's early atmosphere and when plate tectonics and erosion and all that started. Today we're going to talk about relative dating. So we're going to talk about how do we determine how old something is compared to everything else around it. So you got to kind of think of geologists as a detective in these sort of situations. So if you had to figure out what's gone on in a location for the last several million years, what would you want to look at? So to do this, there are three principles or laws that we use for relative dating, and they are uniformitarianism, superposition, and original horizontality. If you remember nothing else from this presentation, remember these three things. So uniformitarianism is the idea that the same processes that shape the Earth's surface today were the ones that were occurring in the geologic past. And we say the present is the key to the past, right? So we talked yesterday about how the erosional process started once we started having water on Earth, right? Well, erosion is still happening, right? We're 3 billion years later, erosion is still important. Deposition is still important as geologic processes. All right, next is the law of superposition. So this is like the entire basis for the idea of relative dating. And this is just saying that the bottom layer is the oldest and each overlying layer gets progressively younger. And this makes sense, right? Like if you drop something on top of a pile, it doesn't fall to the bottom, right? The last thing that got thrown onto a pile of stuff is the thing that is going to be on the top. It's the same with sediments that get deposited to make our rocks. And here we just have a sample. So in this outcrop, the oldest rocks, the stuff that formed the earliest, would be on the bottom and the youngest would be up by the top. And if you made yourself a giant, truly impressive stack of pancakes, the ones you made first would be on the bottom. Again, the stuff you made last would be on the top. Okay? And the last one is original horizontality. So this is the idea that all of our sedimentary and igneous rocks are deposited in flat horizontal layers. So anything that happened to change those layers happened after they were deposited, right? So if you look in the deep ocean, you find layers of clay, and a volcano, you find layers of basalt. So all of these things deposited in layers horizontally. Anything else going on that changed those layers happened after. All right, horizontal layers of sediment. And you see this in rock outcrops. There's a picture here, but you can see it in some outcrops along highways if you happen to be driving past something that hasn't been folded. All right, flat horizontal layers. So when we're talking relative dating, when we find layers that are tilted, we know that a tectonic force has to have acted on those original layers and forced them to move, right? So layers get put down flat. If we have two continents getting smushed together by plate tectonics, then those layers can get folded, bent, turned. So with relative dating, we are determining the age of rock or an event in relation to the ages of other rocks or events around it, right? We are not going absolute age by relative dating, okay? We can't know that this happened 2 billion years ago by relative dating. We can just know event A happened before event B happened before event C. So if you look at the Grand Canyon, we know that the oldest rocks are the stuff way down at the bottom by the Colorado River, and the youngest rocks are the things up at the top by the rim of the canyon. All right? And to add to our original horizontality notion, we do know that the river couldn't start eroding the rocks until after the rocks had been formed, right? Okay, some important things to know with igneous rocks and relative dating. So an extrusion is molten rock that has flowed onto the surface, and it's going to provide another flat layer in the same way that sedimentary rocks will. However, an intrusion, and we've got an animation here, is when rock squeezes into pre-existing layers. So an intrusion is going to be younger than the rock layers that they cross-cut. And it is an exception to the principle of superposition. Now, you might be asking, well, how do I know that this is an intrusion and not a layer that was deposited in that sequence? And the answer is you're going to be looking for contact metamorphism. We're going to talk about that in a couple more slides. Right, this is an example of an igneous intrusion right here. So here's all of our different types of igneous intrusions. We have got a dike, we have a sill, we have a lapilith. And there is volcanic neck up in the top right. So contact metamorphism, this is how you're going to know that your rock is an intrusion and not an extrusion. So remember, from our rock unit, contact metamorphism is going to be a temperature-induced change of our rock to form our metamorphic rock. So with contact metamorphism for our igneous intrusions, you're going to find it along the edges of all your intrusion on all sides, right? So when we do that and put that in a diagram, like this one here, we're going to look at some of these in your classwork today, you will have contact metamorphism identified by these little hashes or whiskers around all of the edges. So in this layer C here, if that was an extrusion, there would only be contact metamorphism along the sides as it's coming through layers B and A and along the bottom. But because there is contact metamorphism on the top as well, we know it was an intrusion. All right, faults. Cracks in the bedrock where tectonic movement has occurred also have to be younger than the rocks that they cross-cut, right? And this makes sense. You can't have a fault in rock that is not there already, right? And they can look very cool. We have this one here, probably normal fault, but you can see this darker layer has dropped right along this line. We also know that folds have to have happened after the rock was originally deposited. So folds when thrusting rock layers cause pre-existing rock layers to overturn. Now, rock that has overturned is going to be the exception to the law of superposition, right? Because if it's been overturned, if it has folded so much that it has flipped over, in that one case, you can get rock where the youngest is on the bottom. All right, so here are the things that happen with our relative dating that help us figure out our sort of sequence of what happened. Faults, intrusions, and folds, they're happening through the rock. They may go from bottom to top, but we know that they have to have happened after the rock was made. All right, a couple more important ones here. So an unconformity is a gap in the geological record. It's caused by the erosion of sediments or rock followed by new deposition. So this is a situation where you've had a bunch of rock layers made. Something uplifted the rock layers, they were eroded, something allowed them to subside, the gradual sinking of a portion of the Earth's crust, substance right there below. After those rocks subsided, they had new sediments deposited on top of them. And it's not unusual, since we have to have uplift to have happened for this to happen, right? To see like some folds where we've had rock that's been folded, moved tectonically, uplifted, eroded, then covered with a horizontal sedimentary layer. Here is our example of that. See, we've got some folds here, and it's really obvious that like these layers and this layer did not happen at the same time, right? This right here, the very obvious break between those two, is our unconformity. In our diagram of a crosscut, we are going to have an unconformity be indicated by a wavy or squiggly line. All right, so we see we've got a whole lot going on here, right? We've got some sedimentary layers that then had an igneous intrusion, and more sedimentary layers, and another igneous intrusion, layer P, and then they were tilted and uplifted and eroded, and then layers H, I, J were deposited. Some sort of other uplifting happened. We have another unconformity. We know we had some erosion. and then some subsidence to bring that back down where more sediments could be deposited to give us layer K. All right, so we're going to list this stuff from oldest to youngest. So first off, we have layer I. And that one probably makes a lot of sense, right? It's at the bottom. We see layer B on either side of this fault here, and layer F on top of that. Like layer I first, easy one. B coming next, also a pretty easy one, right? And F, again, these layers go together. That makes sense. So what happened next? An unconformity. So we have this layer F here has been eroded at the top. And then there was a fault where we see layers F and B on the right of our fault have sank down. We then have the deposition of layer M. Now, we're looking between H and R next, right? We're going R. See how H has contact metamorphism all around it? That tells us that R was there before H. So H is our intrusion. And then up at the top of layer R, that is at the surface, so we have ongoing erosion. All right, so correlation is our process of showing that rocks or geologic events from different places are the same or similar age, and this is the most effective method when we're using relative dating. All right, so when we are correlating rocks, we are looking for similarities in rocks, we are looking for the rock sequence, we are looking for the mineral composition of those rocks, we are looking for color. Often rocks deposited in the same layer, even though they are different. This could be the same type of rock, may have different color depending on what was in their sediments. And we are looking at fossils. So in this section here, we have outcrop A and outcrop B. And if we look between the two of them, we can see we have some layers that correlate, that go together. We have got a limestone layer that is present in both section A and section B, with a sandstone layer and a shale layer right below it that we can see both of and know that, okay, these rock layers, not in the exact same spot, but they've got the same order and they're the same age. And here we've got some correlations from some rocks out west. So we have an example from Grand Canyon National Park, from Zion National Park, and from Bryce Canyon National Park. I've only been to Grand Canyon. The other two are on my bucket list. I don't know about you guys. But we have some different layers here. Some old rocks from the Permian that are present in both the Grand Canyon and Zion National Park. And then we look and we have some Jurassic rocks that are present in both Zion and Bryce Canyon National Park. So we can get the relative ages of the rock depositions in some of these national parks by correlating them to the others. All right, next up, one of the coolest parts of our earth science class, we got fossils. All right, we got some examples here, a bunch of marine stuff, lots of shells, lots of critters with shells, right? All right, so fossils are just the preserved remains or traces of ancient life. So bones, shells, footprints, and organic compounds are all things that can be fossilized, although harder things like bones and shells you're going to see a lot more often. So one important thing to know for fossils, and you can see this in your page 8 and 9, are index fossils. So index fossils are important fossils used to define and identify geologic periods, and this is a really great way to correlate rocks from different places, because to be considered a good index fossil, there's two criteria it has to meet. So the first one is it has to have existed over a large geographic area. So it has to have been like all over the place. So we call that a large horizontal distribution because it's going to end up in the same, like layers from the same period of time. And the organism existed over a short time. So we're looking for a small vertical distribution. So something that was short-lived in geologic terms, but existed everywhere. We could argue that several 100,000 years from now, if humans have gone extinct, humans will make great index fossils because we are living over a large geographic area, and in terms of the 4.6 billion year history of this planet, we've been around for a relatively short amount of time. All right, so which of these fossils would be the best index fossil? So take a look here. We've got some that are present in more than one layer. We have many that are present in more than one outcrop. But there's only really one that is present in all, and that is our little round snail-looking shell that's in the second from top layer of sandstone in all 4 outcrops. Our index fossil in New York State is the Eurypterid. All right, so geologic time markers, or a key bed, are deposits that are spread over a large area that represent a specific date. So there's 2 things that really give us good examples of this, and they are volcanic ash deposits and meteorite impacts. And that's because those are like distinct events, right? A volcanic eruption may happen over the course of days or weeks, but it happens over a short period of time relative to the history of the Earth, right? A meteorite impact, similarly, that's going to be one moment where something impacts and sends up a bunch of sediment into the air that will settle and leave a layer that tells us this big event happened at this time. So here we have a volcanic ash layer separating these 2 other rock layers here. All right, this is the end of our relative dating notes. Tomorrow we are going to talk about sequence of events and just do a lot of practice with those. And today's assignment, you've got some correlation and you've got some finding index fossils in your page 8 and 9 of your reference tables.